In this last part of Chapter 2 on quantum, we're now going to talk about how electrons behave. So we just learned about diffraction with light. So if we expect electrons to act like particles, then we should kind of see the particle type behavior, where if I shine a bunch of electrons at a slit, then it should on the film produce just two bright spots if there's two slits. But what actually happens is that when we shine electrons through a slit, two slits, they produce an interference pattern. So we get regions of destructive interference where there's a dark spot, and constructive interference where there is a bright spot. And that is kind of different. So they produce an interference pattern. So in this way, electrons are acting like light. So electrons can actually behave like particles, having like matter where it has a mass and volume, and we can know its position. From an energy perspective, knowing its wavelength and frequency and energy, then we can see its interference pattern. But what's really weird is we can't see both at the same time. So either electrons end up acting like a particle, or they end up acting like a light wave. So that's really strange, a really strange phenomenon. So these are complementary properties, and so the more you know about one of them, the less you know about the other. And that leads us into Heisenberg uncertainty principle, which says that the uncertainty in the electron's position times the uncertainty in its velocity is greater than Planck's constant over 4 pi. So basically, this is a constant, that's a value. So if I learn about how the position of an electron, so I can really narrow in my tools so that the precision of that is really really small, then my uncertainty in the velocity goes up. And then if I try to really narrow in on the velocity, then the position goes up. So the more you know about one, then the less you know about the other. So that gets us into determinacy and indeterminacy, which is if we have something that like familiar to us, like a ball, its path is determined by the forces of nature. So if I throw a ball, then I can, by looking at the velocity and position and forces on it, I can predict where it's going to go. Whereas with electrons, since I can't know position and velocity really well at the same time, we can't know its path, so it's indeterminate. So we can only predict its probability of being in a certain place at a certain time. So this is what it is for electrons. So before, with Bohr's model, we basically were like, okay, electrons are in this orbit, kind of like planets, right? It's in this orbit. We know it's there, but in reality, it's in this probability distribution where we have areas in the middle here where it's highly likely electron is, but it could be further out and it could be down here, you know. And so this gets into quantum mechanics and the Schrödinger equation. Schrödinger's equation helps us to calculate the probability of finding an electron with a certain amount of energy, so that means in a certain spot within an atom. And so he uses this chi squared, which represents an orbital. And in that is the probability that an electron is going to be found in that area. When the Schrödinger equation gets solved, we use the different numbers from this wave function to help us in like identifying a certain electron. We can learn the size, shape, and orientation of an electron in the atom. So there are 4 quantum numbers that we get from the wave function, which is solved from the Schrödinger equation. The first one is the principal quantum number n, and this helps us to know the energy level as well as the position. The angular momentum quantum number L is the orbital type. So what does the orbital, like basically what's the shape? The magnetic quantum number M sub L, which is the position or the orientation with respect to an XYZ plot. And then the spin quantum number, which is which direction is the electron moving. It's the direction of motion. These are important, and you'll need to know what these mean, like not just memorizing them, but really understand what this is, because we can use this to basically get a roadmap to where an electron lives within an atom. So the energy quantum number, the principal one, this is the standard one that we thought about with the Bohr model, where we had, these different energy levels and distances from the nucleus. So it's similar. So these can be any whole number equal to or greater than 1. So starting closest to the nucleus is n equals 1. Then we get n equals 2, n equals 3. And keep in mind, this is using the wave function, so it's a probability of being near that orbit, right? So that's the orbital. And it helps us to know how the overall size of where an electron is and its energy. So the further out you go, the bigger the distance is from the nucleus and as larger the energy is. So the larger the value of n, the more energy, and the larger the orbital. And keep in mind that we define energies as being negative. So as you get higher in energy, you're getting less and less negative, so you're getting closer to 0. And when we hit 0, that's when an electron basically is no longer a part of the atom anymore. So being n equals 1 here, that means we're all the way down at the bottom and with the most negative energy. So basically the energy, and then you also see here, as we go from n equals 1 to n equals 2, we have a pretty big gap. Then we get smaller, 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 and they get infinitesimally closer. So the energy is the gaps between the energy levels get smaller as you get farther away from the nucleus. And the energy of each of these orbitals can be related by this equation. So negative 2.18 times 10 to the negative 18 joules times 1 over the energy level squared. The momentum quantum number L helps us to know the shape of an orbital. Okay, and this can have values from 0 to n minus 1. So all levels will have an L value of 0, and some of them can go higher depending on what energy level you're at. So every L value we designate with a shape, we designate with a letter which designates a shape. So that's fun. So when we have L values of 0, that's our s orbitals, and they look like a sphere. When we have L equals 1, so L equals 1, that means we have p orbitals, and they look like these dumbbells here. When we have d orbitals, that means L equals 2, and they look like these 4-leaf clovers. And then with F, that means L equals 3, and then they look like this, like 8 balloons tied together in the center. So you'll need to know, like L equals 0, that means s orbitals, and s orbitals look like a sphere. L equals 1, p orbitals, and they look like a dumbbell. And we're going to be carrying on with these and throughout, honestly, a lot of chemistry. And so it's easy to forget that this is where they came from, but it all helps chemists and physicists to understand where the electrons are within the atom. The magnetic quantum number M sub L is the positional orientation. And so this tells us like where in space is the electron, or is the orbital pointing. So this value goes from negative L to positive L, and it includes 0. So when I have L equals 1, then the values of M sub L are negative 1, 0, and positive 1. So I would count each of these numbers, each of these digits, and that will tell me how many orbitals I have. So 1, 2, 3 means I have 3 orbitals that are all p shape. So this is what they look like, one on the x-axis, one on the y-axis, one on the z-axis. Now the spin quantum number here tells you at which direction the electrons are spinning. So, and for this situation, all of the electrons are going to be given the same magnitude, but they're just going to have a different sign. So it could either be given a spin up value, which is a positive 1/2, or a spin down, which we'll call negative 1/2. And the 1/2 comes from basically what makes this able to work in mathematically be solved. So every set of N, L, and ML describes an orbital. When an orbital has the same N value, we say they're in the same principal energy level, and then each orbital that has the same L value has the same sublevel. So when we think about N equals 2, which is right up here, there are 2 sublevels. So we have the option where L, which has to be less than N minus 1. So it could either be, if N equals 2, then one option is for it to be 1, and another option is for it to be 0. So when L is 0, we know that's an S orbital. So since it is in the second level, we say it's 2s. For L equals 1, the only M sub L value, because remember M sub L has to be between positive and negative L, so that would be, the only option is 0. So M sub L, just having there be one value, means that there's one orbital in the 2s level. So that corresponds to this one right here, this little box. For L equals 1, for L equals 1, that's a p sublevel. So we would have these be in the 2p level since there's since the energy level is 2. Now for L has to be between positive and negative, or M sub L has to be between positive and negative L. So we're going to have, since L is 1, we'll have -1, 0, and +1. So there are 3 values, so those are the 3 p orbitals shown here. So now we're going to practice a little bit. So what are the quantum numbers and names for the orbitals in the N equals 4 principal level? And then how many of them are there? So for N equals 4, we have L values that are 3, 2, 1, and 0. So we would have L equals 0 is S, so we'll have 4s. L equals 1 is P, so 4P. L equals 2 is D, 4D. And L equals 3 is F, so 4F. For each of these, so for the M sub L, that will tell us how many of those orbitals there are. For M sub L of 0, there's only M sub L equals 0, so just 1. So 1, 2s. For M sub L equals, for L equals 1, we have M sub L -1, 0, +1, so 3 values. So 3 4p orbitals. For L equals 2, we have M equals -2, -1, 0, +1, and +2. So there's 5. And L equals 3, we'll have -3, -2, -1, 0, +1, +2, +3. So count those up. 3, 4, 5, 6, 7. So 7 of those. So total what we have is 16. So list the quantum numbers associated with all of the 5D orbitals. How many are there? So for 5D, we know that N equals this number here, 5. So for N equals 5, we have L equals 4, 3, 2, 1, 0. So we'll count up until we get to D. So 0 is S, then P, then D. So for this case, 5D, L equals 2. And then we have, because there are L equals 2, M sub L could be -2, -1, 0, +1, +2. So there are 5, 1, 2, 3, 4, 5, 5d orbitals. Sorry, we don't need that. So these sets of quantum numbers are each supposed to specify an orbital. One set, however, is erroneous, so which one and why? So you'll do that for all of these, and then you'll figure it out. So I'll let you pause and try. So first thing we want to check is between N and L. So it has to be less than, at least one less than, and it could be down to 0. So this one checks out. This set checks out, for those ones anyway. That checks out. That checks out. So now we want to check the L and the ML. So that has to be between positive and negative of the L value. So this one works. L to negative, L equals 1 and ML equals -1, that works. 0, 0, that works. L equals 1. M sub L has to be between negative and +1, so that one does not work. So this one is erroneous. Checking out the other ones, it looks like these are repeats, so we're not going to do them. But for this one, we want to fix the quantum number that doesn't work. So we'll look at N to L. That doesn't work because L needs to be less than N. So M sub L is +2, so we'll make L 2. Here we have N equals 2, L equals 1, that works. M sub L equals -2, no. So we can change that to ML. It could be anywhere between positive to -1. So let's go with -1. But it could be 0. It could be also +1. N equals 1, L equals 1. Nope, L can't be the same. It has to be less than, so we'll call it 0, and then that works out. Now we're going to switch to talk about how this model explains the atomic spectra that we talked about earlier. So we know that when we excite an electron, it gets enough energy to transition from a low energy to a high energy level. So for example, down here, we get some energy in, and we can transition up. After it's up high, it's going to relax down into a lower energy level. But because the energy we put into it, that has to go somewhere when it relaxes. So when it relaxes down to a lower energy, it's going to emit a photon. Now that photon will have a wavelength and a frequency, and that's going to correspond to this energy change. And that will correspond to a certain wavelength or color. So for hydrogen, which is easily, well, quote unquote, easily calculated its energy levels using the Schrodinger equation, we can basically predict what colors we should be able to get from the excitation of the electrons in hydrogen. So if we have n energy levels, then there are n-1 possible transitions it can do. So that's how many emission lines we should get. And this is very consistent with the Bohr model as well. And it works really well when we have a one electron system like in hydrogen, and once you get more complicated ones, it gets a lot trickier. But we can predict the wavelength of light from the difference between these energy levels. So the electron energy difference is going to be the final state minus the initial state. So that's going to be, with the calculation we'll use, is delta E equals -2.18 times 10 to the -18 joules times 1 over NF squared minus 1 over NI squared. So I ultimately just call it F squared minus I squared. So you take the final position that it ended at, subtract 1 over the initial, and make sure you square those. So now we're going to practice it. So we're going to figure out the wavelength of light emitted when it goes from an n equals 6 to an n equals 5 energy level. So what we'll do is we're just going to plug in our delta E equation. So we'll go -2.18 times 10 to the -18, and and that's in joules, times 1 over F squared, so final minus initial. Now the final here is 5, it ended at 5, minus 1 over 6 squared, which is where it started. Now in your calculator, it's really important that I actually would do this math first. 1 over 5 squared, so 1 over 25 minus 1 over 36 to find out what that value is, and then multiply it by that constant. Your calculator will do the math if you put it in it correctly. So what we get for the delta E of my electron equals negative 2.664 times 10 to the negative 20th joules. So if we want to know the light that gets emitted, then we're going to have to do some thinking about it. So I know that, so we had an electron, it went from n equals 6 down to 5. So it lost energy, it got more stable, hence why it's a negative value. That makes sense. But that energy got transitioned to the light. So we have the electron lost energy, which means it gave it to the photon. So the energy of the photon equals the negative delta E of the electron, which is going to be, in this case, we'll just take the opposite, and it will be a positive 2.664 times 10 to the negative 20 joules. So now we have a photon situation, and we know that the electron energy, of a photon equals hc over lambda, or h nu. So we can solve for lambda by cross multiplying. We get lambda equals hc over energy. And so when we plug that in, we get 6.626 times 10 to the negative 34 joules times seconds, times 3 times 10 to the 8 meters per second, divided by that energy, 2.664 times 10 to the negative 20th joules. And what we get for our lambda is 7.646 times 10 to the negative 6 meters. So when we multiply that by there being 10 to the 9 nanometers per meter, our calculation is 7,460 nanometers. So the big takeaway here is when an electron is relaxing, the energy that the electron lost gets transitioned to a photon, so we just take the negative. Also, you can never have a negative length as far as a wavelength goes, so if you do get one, then that's where it came from, was up here, so you just got to go back and make sure you make a little note of that. So now we want to find out what's the wavelength of light that needs to get absorbed when an electron goes from n equals 2 to n equals 7. So now we have n equals 2 going up to n equals 7. So we are going to need to shine a light that will excite the electron. So now the energy that's getting absorbed is going to go into the atom. So the energy of the electron equals negative 2.18 times 10 to the negative 18 joules times final minus initial squared, 1 over that. So final is 7 squared minus initial is 2 squared. Plug that in your calculator and you get the energy of our electron equals 5.01 times 10 to the negative 19 joules. Okay, so now in this case, since we're exciting it, the energy from the electron came from the photon. So we can now say energy of the photon equals hc over lambda. Solve for the wavelength, so lambda equals hc over energy. So we'll put in our Planck's constant times our speed of light. There's a baby in the background. Our energy of our photon needs to be 5.01 times 10 to the negative 19 joules. Solve for wavelength. So now our wavelength is 3.97 times 10 to the negative 7 meters. Convert to nanometers, and we get 397 nanometers. So as long as our wavelength has that kind of energy, we'll be able to excite that electron all the way up to the 7th energy level. Here's another one. We have another relaxing situation. So electron in n equals 6 relaxes to a lower energy level, emitting a wavelength of 93.8 nanometers. So we want to find out where did it go to. So what's that final level? So this is the hardest it could get, which is where you have to basically solve for one of the levels. So we got to go backwards. We have the wavelength. So now I can, of course we don't want our wavelength in nanometers, so I'm going to need to go 93.8 nanometers into meters. So I have a billion nanometers in 1 meter, which gives me 9.38 times 10 to the negative 8 meters. So solving for the energy of my photon, I'm going to do hc over lambda, so 6.626 times 10 to the negative 34 joules times seconds times speed of light divided by this wavelength. So we get our energy of our photon equals 2.12 times 10 to the negative 18 joules. So since it is relaxing, so our photon came from being passed from an electron that got relaxed. So the energy of my electron is going to be the negative, or the change in energy of my electron will be the negative of my electron energy from my photon. So that'll be a negative. So my electron lost 2.12 times 10 to the negative 18 joules. That's an 8. So now we want to solve for F here. So I'm going to have the change in energy of my electron equals negative 2.18 times 10 to the negative 18. Oops. Times 1 over the final squared minus 1 over the initial squared. So it was in n equals 6, and we're trying to find out where did it relax to. So I'm trying to find out final. So in order to not have to write out a billion numbers, I'm going to solve for final. I'm going to first get rid of this number in front. So I'm going to divide both sides by 2.18 times 10 to the negative 18 on both sides. So that goes away. Now we have our change in energy of our electron divided by negative 2.18 times 10 to the negative 18 equals 1 over f squared minus 1 over I squared. So now I can move this whole thing over by adding. So now I'm going to plug in numbers after I move that in. So I'm going to have negative, or delta E of the electron, which is negative 2.12 times 10 to the negative 18 joules divided by negative 2.18 times 10 to the negative 18 joules plus 1 over 6 squared equals 1 over f squared. Now this whole thing equals 1.00025, so that's what that whole 1 over f squared equals. So we'd want to inverse it, both sides, to get this f squared on top and then square root it. And when we do that, we see that the final state is n equals 1. So now that we've talked about jumping between energy levels, we're going to actually talk about what do these shapes actually look like. and what happens as you go from an energy level of n equals 1 to an energy level of n equals like 5. What does that actually mean? So we want to go back to the chi-squared definition, which is a probability density. So the probability of finding an electron at any given point. And as we get further and further away from the nucleus, the likelihood of finding it decreases. Which means that we are, based on this, we're most likely to find the electrons closest to the nucleus, which is actually kind of a weird concept. So maximum probability, maximum at most probable radius. We can see for a 1s orbital, we have this probability density that shows a likelihood of finding it in a spherical shape. So that's where the s comes from, and the shape of an s orbital comes from. And when we see these functions, as we start to get more and more complex, we'll see that we'll get these nodes, and that's where the likelihood of finding an electron drops to 0. So that's where the kind of the distinction between each energy level is. The radial distribution function tells us the probability, so that is just chi, so not chi-squared. And that helps us to actually really see a little bit better about where an actual radius is versus being at the nucleus. So when we plot that, we see for hydrogen atom, the most probable distance, so the peak of the radial probability is over here at 52.9 picometers. As we get larger n values, we'll start to see some of those nodes. So our function shows us that there's a, and remember this is probability density, so chi-squared, and so it's going to really shoot up at 0 by the nucleus, but see there's the node, and that will translate into the radial probability. You'll still see a node there. And now we'll see, okay, here's that little bump, there's the 1s. This little bump, there's the 2s distance. And here we have 1s, 2s, 2s, and 3s right there. And so that's where we can predict those distances of each energy level. So starting with the s orbital, so that's when L equals 0. This is our lowest energy orbital. It's spherical, and it has n minus 1 nodes. So if we're on the 1s level, n equals 1, then we'll have 0 nodes. If we're on n equals 2, we'll have 1 node, and we saw that on the last slide. When we get to L equals 1, this is our p orbitals. And there are, for every n level, there are 3 p orbitals, because m sub L is from negative to positive L. And so each of these values represent an orientation that one of the p orbitals could be in. So we have px, py, and pz, and so here we see the x, the y, and the z. They're the same shape, but it's just going to be a different way that it's oriented. These ones have 2 lobes, and this is going to be the next highest energy level. There's always going to be a node at the nucleus for this one. The next one is the L equals 2, which is our d orbital. There are 5 d orbitals that come from our m sub L values. And so they are now on planes since we get into 2D. So we have the xz, the yz, the xy planes. Then we have this kind of like crisscross between the x and the y planes, and then this funky little, it looks like a p orbital with a donut. It's an interesting one. So that one's on the z-axis. And these look like 4-leaf clovers. So they're for the most part, 4 lobes. And then there's going to be more nodes. So you can see that each of these ones has 2 planes where it has been cut. Our f orbitals, they get really tricky. I don't expect you to know exactly what these look like, just they're more complicated, more nodes. they mostly have 8 lobes. There are 7 f orbitals coming from our m sub l value, so 7 orientations. And you'll see for all of them that there's quite a bit more nodes for the f orbitals. Okay, now we're going to do some practice problems. So for the first one, we want to know, what do the atom's 2 p orbitals have in common? So thinking about all of the p orbitals in here have the same L value. And because they're all in the 2p, then they have the same N value. But what's different is that the m sub l's are going to be different because they're oriented in a different way, so they will not have the same m sub l value. To describe this, N, L, and ML quantum numbers, 2, 1, and negative 1. So 2 is the N, 1 is the L, and negative 1 is the m sub l. So this would be an energy level of 2. L of 1 equals a p orbital, and negative 1 is just an orientation, so these are p. This is a type of p orbital. Okay, so then we have N is 3, so we have 3. L is p here when it's 1, and then this is an orientation, so this is also a p orbital. Here we have 3, 0, and 0, so we have a 3 energy level. L of 0 equals s, so this is an s orbital. And there's just one orientation, so that's all it could be. If an orbital has L as 3, this orbital could exist in the N3 shell. So remember that L has to be less than N minus 1. So if N is 3, then L has to be less than or equal to that, so 2. So this cannot work because the first possibility where L equals 3 would have to be the energy shell of 4. So that does not work. Okay, the last thing is we want to talk about phases. So every orbital has a phase. They're determined from those wave functions we talked about, which are mathematically determined. So because of that, the wave is going to fluctuate between positive and negative values, and the nodes are where a wave function equals 0. So the sign of the wave is called its phase, and when we have waves that are in phase, then they have the same sign, and when they're out of phase, they have opposite signs. So when I have a 1s orbital, what it looks like, it has no nodes, so it just looks like kind of like the top part of a sine wave. Or if we had 2 barriers here, it would be fluctuating. When we have a p orbital, we have a node here. And so what that ends up looking like is having a positive side here and a negative side over here. So keep that in mind as we do more stuff with this later on.